In lecture 14, we're going to be covering the inverse functions, particularly the inverse sine, inverse cosine, and inverse tangent. These tools become particularly useful in solving equations that involve trigonometric functions. So our first objective is going to be to find exact values for the inverse sine function, but then we'll also be able to find approximate values of inverse sine functions using our calculators. We're going to use some properties of inverse functions to find the exact values for certain composite functions. For example, the inverse sine of a cosine, or the sine of an inverse cosine, and so forth. Then we're going to find inverse functions for other trigonometric functions, and then use those to solve equations that involve inverse trigonometric functions. And then in future lectures, we're going to be talking about solving just general trigonometric equations, that is, equations involving sine, cosine, tangent, and how we use those sine functions or inverse functions to solve those. But first, let's begin by reviewing what we know about inverse functions, or refreshing our memory from possibly previous math courses you've had. The first thing we want to talk about is what kinds of functions actually have an inverse. A function is said to be one, two, I'll just write it out, 1, 2, 1, if for every output of the function there exists exactly one input that produces it. Meaning that, for example, if you know the function's output was a specific number, you know there was one and only one input that would give you that output. Now, many functions are not one-to-one. The way that you can tell whether or not a function is one-to-one is by looking at, well, one way to look at it is by looking at its graph. And one way to do that is by what's called the horizontal line test. What the horizontal line test says is that if I draw any horizontal line at all on a graph, if it intersects the graph at exactly one point at every horizontal line, then it's one-to-one. On the other hand, if there is ever any horizontal line that intersects at more than one place on the graph, then that function is not one-to-one. This one over here, again, all I'm doing is just sketching a few horizontal lines on here to determine the fact that they all intersect at exactly one place. So I would call that a one-to-one function. The reason it's important is, notice that, for example, the height of this point, the height of this point, and the height of this point are all the same. And if it's the same height, that means you've got multiple x values that give the same function output. Now, the reason why it's important to note that when talking about inverse functions is inverse functions will always try to find the input if you know the output of the function. And since all three of these points on this middle graph have the same height, you're not going to get a unique output. So the only types of functions that have inverses are ones that are one-to-one. Okay, so every one-to-one function has an inverse function, which we denote by f of x, f to the minus 1. Right, we just put a minus 1 in the superscript, such that if you take and apply the inverse function to the function, they cancel each other out and give you back x. And vice versa. If you apply the function to the inverse function, you get x. They cancel each other out. Okay? Now, in this example, if you start with f of x is equal to x cubed, it turns out that the inverse function f inverse of x is cube root of x. In the second example, the inverse function that will undo that operation. Again, what I'm thinking of with inverses, and I'm thinking of the function that undoes whatever the actual function does to it. So if you take a number, cube it, what will get you back to the number you started with? A cube root. If you take a number, multiply it by 3, and then subtract 2 from that, how do you get back to where you started? Turns out it's x plus 2 all divided by 3. Now we can take a look at where we get that function. In general, there's a nice little algebraic technique to find inverse functions once you know they're one-to-one. What you can do to find the inverse function is to take the f of x and replace it with y, and then swap all the x's and y's, and then solve for y. What I mean by swap all the x's for y's is everywhere there's an x, put a y. Everywhere there's a y, put an x, and then solve for y. And then once you replace y with f inverse, you found the inverse function. So like this guy, y is equal to 3x minus 2. If you swap all the x's and y's, you end up with x is equal to 3y minus 2. Everywhere there's an x, put a y. Everywhere there's a y, put an x. Now solve for y. So move the 2 to the other side. You have x plus 2 is equal to 3y. Divide both sides by 3. And y is equal to x plus 2 over 3, or f inverse of x, that is the inverse function of this guy, is x plus 2 all divided by 3. And again, the inverse function undoes the original function. Now, of course, what we want to do is now apply this concept of finding inverse functions to our trigonometric functions. But we run into a problem. If you look at the sine function, you'll notice that we can't really have an inverse function. Nothing's going to undo sine as long as we consider the whole function, because look at this. Is it one-to-one? It's not, because if you draw a horizontal line, guess what? You've got not only more than one point that it crosses at, but you've got infinitely many, because this thing goes on forever in both directions. So it's not one-to-one. So how do we find an inverse? And the answer is restrict the domain. In other words, when we ask for the value that, or I guess the function that undoes sine, we don't want a value that gives me an output over every real number. What I'm going to do is I'm going to cut this function off right here and right here, and only look at this part of the curve right here. If I only consider the highlighted region, it's one-to-one. Right? So inverse sine is going to be defined over this interval instead of over the entire real number set. So consider now this function, which is y is equal to sine of x, such that x is between negative pi over 2 and positive pi over 2 inclusive. Okay? Now we will define y equals sine inverse of x to mean x equals sine of y, meaning it's the same thing as if I had written x is equal to sine of y. Think of it this way. If I plug in a number right here for x, for example, I say sine inverse of 1, I'm looking for the angle such that sine of y equals the x that I'm taking the inverse of. Okay? And in these cases, recognize that here's x, here's y. X goes from negative pi over 2 to positive pi over 2, and y, actually I get this backwards. In my function, the input of sine goes from negative pi over 2 to positive pi over 2, and the output goes from negative 1 to 1. Now what does that mean I can plug in here inside this? That means that the set of values that I can get an inverse for are these values here, namely x can go from negative 1 to positive 1, and then the possible angles, the output of the sine inverse function, is going to be negative pi over 2 to positive pi over 2. This sine to the negative 1 of x is called the inverse sine, sometimes called also the arc sine, A-R-C-S-I-N-E. To find the graph of the inverse sine of x, recall that the inverse function swaps the x's and the y's. So every point on this curve will become a point y comma x on y equals sine inverse of x. It swaps the x and the y, right? Which means that, for example, this point right here says that sine of pi over 2 that's negative is equal to negative 1, right? Well, that also says that negative pi over 2 is equal to the sine inverse of negative 1. All right, that's what the definition of the inverse sine tells us. So the point negative pi over 2 comma negative 1 is on the sine function, okay, but now the point negative 1 comma negative pi over 2 is on the inverse sine function. Okay, so where is negative 1, negative pi over 2? Well, negative 1 is about here, and negative pi over 2 is like negative 1.7. So I've got some stuff in the way here. I tell you what, I'm going to be tricky with my tool, and let's just drag this over here. Now I can come in here and draw and say this point right roughly here is on that new curve. And you repeat this process with every point on here. What you end up doing is actually reflecting your sine wave across the y equals x line. So like this point here becomes this point here. It kind of goes away from it. There's your inverse sine of x function. It's the sine wave restricted to negative pi over 2 to positive pi over 2, reflected about the line y equals x. To make sure we understand the sine inverse function, or the arc sine function, let's think through what a few of these examples might look like. The first one says, find the exact value of y equals sine inverse of negative 1. Well, this says the same thing as sine inverse of what angle y would give me a 1. On, right, y goes from negative pi over 2 to positive pi over 2. The output of a sine inverse function is always going to be between these two numbers. So which angle in radians has a sine value of 1? And the answer is pi over 2. So y is equal to pi over 2. Right? And you remember from your unit circle definition, sine is the y coordinate. Right? So this right here is where y is equal to 1. Did I say that wrong? This right here is where y is equal to 1. Right? Because height of 1. Alright, let's try the next one. Find the exact value of sine inverse of negative square root of 2 over 2. Okay, well, this says sine of what angle gives me negative square root of 2 over 2. And again, we're looking at something from negative pi over 2, which is down here, up to positive pi over 2. Now, square root of 2 over 2 is right there at the negative 45-degree angle, or negative pi over 4 gives me a negative square root of 2 over 2. Okay? and that's the coordinates of that point. Square root of 2 over 2, common negative square root of 2 over 2. Your sine is the y coordinate, so that means the answer is negative pi over 4. Really, it's easy if you get the unit circle definition down. You know your points on the unit circle. You know all the coordinates for our special families of angles. Then the inverse function is just the reverse question of what we used to ask, where instead of asking, what's the y coordinate for a given angle, we're now asking what's the angle for a given y coordinate. Okay, what about the exact value of sine inverse of 1.8? Okay, well, think about this. Sine of what angle gives me 1.8? And if you think about that for a second, you realize we have a problem, right? Where are all the outputs? Where are all the y coordinates? Well, the y coordinates range from -1 to 1. It's not possible to get a 1.8 out of a sine function, so it is undefined. You can also see it's undefined by going back and looking at the definition of the inverse sine function. Up here at the top, which says that the only things that you can plug in inside are x values from -1 to +1. If you try to plug something in outside of that, you're going to get an undefined value, which is exactly what happened here. All right, what if we wanted to find the approximate value of a sine inverse function? So, for example, I wanted to do sine of what angle is equal to 1/3. You'll notice on our unit circle for special families of angles, we do not have a 1/3 as a y coordinate anywhere on that graph. So the best we can do is use a calculator. Now, you may have a different type of calculator out there, but you're looking for either the sine to the -1 or the a sine button on your calculator. Make sure it's in radian mode before you get an answer out of it. But when you plug in this guy right here, sine inverse of 1/3, you should get, rounded to the nearest hundredth place, a 0.34 radians as your answer. So you want to test that out with your calculator. Make sure you're able to do that. If you have any problems at all using your calculator, just send your instructor an email. Make sure they know what type of calculator that you are using. On the next problem, we're asked to evaluate a composite function, meaning the sine inverse of a sine. Now, when you take a sine inverse of a sine, your intuition should tell you those things will cancel each other out. Okay? But note, they only cancel if theta is between -pi/2 and +pi/2. That's a theta. That is the angle, even, or I could have said x just as well in there. In fact, I'll tell you what, let's erase that. Now, in this case, I don't even have to evaluate the function. I just recognize the fact that pi/8 is about right here. Right? Taking the sine of that will give me the y coordinate of that point right there. I don't even have to find what that y coordinate is, because what I would do is then take the y coordinate and say, what angle gives me that y coordinate? That's the sine inverse part of that question. And clearly, this has to be then just pi/8. Right? Because the sine says what's the y coordinate of the point where that angle intersects the unit circle, and then sine inverse says what's the angle between -pi/2 and +pi/2 that gives me that y coordinate. And in this case, it was pi/8 that did it. If you look at the second question, you'll realize that that doesn't work exactly the same way, because where is 5pi/8? Well, this angle right here is pi/2, or 4pi/8, right? I'm just saying, in terms of pi over 8, you get 4 of them, then you're up here at the pi over 2 place. So 5 pi over 8 is just a little bit past there. Okay, so when we're looking at my unit circle here, this inside part here says find the y coordinate where that angle intersects. Right? And if I take the inverse sine of that, I am not going to get that same 5 pi over 8 out, because 5 pi over 8 is not between negative pi over 2 and positive pi over 2. But I can still figure it out. And here's how I figure it out. I'll do this in a slightly different color here. If I go straight across, there's a point right here that has that same y coordinate because it has the same height of that point. What is this angle going to be? Well, you use the symmetry of the circle. Since this is the same height, it's going to be the same angle only on the other side of the y-axis. Can you tell me what this angle right here is? Well, since the y-axis right here was 4 pi over 8, this right here has to be pi over 8. Did you catch that? Because it's 4 pi over 8 plus one more to give me 5 pi over 8. So if I go pi over 8 this way, what if I went pi over 8 this way? What does that leave this angle right here to be? It's 4 pi over 8 minus pi over 8, which is 3 pi over 8. That's going to be what you get when you do the sine inverse of the sine. Again, they cancel if you're in the domain of the sine inverse function, but they won't cancel otherwise. Alright, changing gears and looking at the cosine function, we can ask the same kind of question as to what undoes the cosine function, but you notice we run into the exact same problem as before. Cosine is not one-to-one because you can find a horizontal line that hits the function in more than one place. So guess what we do? We restrict the domain again. But this time you'll notice if I were to have tried here and here, notice it's still not one-to-one in there. Right? So I tell you what, let's do. Let's not restrict it there, but let's restrict it in a slightly different place. What if we did it from, say, here to here? Notice then the function between 0 and pi turns out to be 1-to-1. Following the same reasoning as before, we can look at the graph of an inverse function of cosine by reflecting it about this line y is equal to x. If we reflect it there, then this point becomes this point over here, reflected. It's going to intersect here, and then somewhere up here at pi over 2, remember pi over 2 is about 1.7. And then this point, which is over here at pi negative 1, is going to be negative 1 and up pi, which probably is somewhere up here. So the curve for the inverse cosine looks something like this. Poorly placed on the screen since it overlaps some of the text, but that's the graph. And by definition, what we mean is, as before, if I say y equals cosine inverse of x, I mean cosine of what angle? Cosine of what angle here gives me the x that I'm plugging in inside. It's called the inverse cosine, or in some context we refer to it as the arc cosine. And so that's what the graph would then look like. So at the top of the next page of your notes, what you have is just a summary comparing y equals sine inverse and y equals cosine inverse. Remember that the inputs, the numbers that go in for x, are all the possible outputs of sine and cosine. And you'll remember that you always get a coordinate on the outside of the unit circle, either the x-coordinate for cosine, y-coordinate for sine, and those range from -1 to +1. So the only things you can plug into a sine inverse function will be a number from -1 up to +1. Same thing for cosine inverse. But the outputs are different. The outputs for the sine inverse function range from -π/2 to +π/2, or the right half plane. Remember, the outputs of the inverse trig functions are angles. Okay, the inputs are real numbers from -1 to +1. And the angles that you get out of a sine inverse are the right half plane. The outputs you get from an inverse cosine function is the upper half plane. That is, any angle in the upper half, from 0 to +π. And again, it goes back to the reason of, in order to have an inverse function, you have to have a one-to-one function. So think about exact value of y equals cosine inverse of 0. Okay, this is asking what angle gives 0 when you take the cosine. All right, cosine of what gives me 0? And the what has to here be between 0 and pi. And remember, again, I think of the unit circle in my head. Where is the x-coordinate 0 in the upper half plane? It's up here, right? Which means the answer is π/2. Alright, so cosine inverse of -√3/2. We're asking, okay, in the upper half plane, from -1 to +1, where is the x-coordinate equal to -√3/2? X-coordinate, right? Which is going to be somewhere over here. In fact, it's more than halfway. It's this guy right here. And if you have to, go ahead and look at the unit circle table that you've got. So what angle is that? Well, I know that this is 5π/6. So that's the answer to the inverse cosine of -√3/2. Now, how did I know that? Is that I remember and I've studied and I've learned the trig function values for my special family of angles. Okay? Alright, last one. We are going to look at the cosine inverse of -0.44 in radians. So I'm going to go to my calculator and use either the cosine inverse function, or if my calculator writes it this way, it'd be ACOS for arc cosine, and I do the cosine inverse of -0.44 or arc cosine of -0.44, and I should get a 2.03. Again, make sure you're in radian mode or you'll get a different answer out of this function. Last but certainly not least, we're going to talk about the inverse tangent function. You remember the inverse tangent function is a periodic function that follows this shape but repeats itself over and over and over again. Again, if you look at the entire tangent function, you'll see that it is defined over the entire real number set and then would not be one-to-one. However, you can restrict the domain, and it's very natural in this case to choose the asymptotes so that your restricted function is just this guy right here, and he is one-to-one. And the inverse tangent function would be defined in the exact same way so that you're trying to find what angle gives you that value that you're plugging into the inverse tangent function. But keep in mind, it's between negative pi over 2 and positive pi over 2. All right, so your right half plane is going to be your output for an inverse trig function. It's like sine. It behaves like the arc sine function in that regard. But interestingly enough, if you look at the picture, remember that the sine function and the cosine function only give you outputs from -1 to 1, right? So that their inverse functions can only have -1 to 1 plugged into them. With tangent, however, this thing goes infinitely high and infinitely low, so that you can actually plug in to the inverse tangent function any number and you'll get an output. In this case, in the example that I've got right here, what I'm going to do is I'm going to find the inverse trig function for negative square root of 3. So tangent of what angle between negative pi over 2 and positive pi over 2 gives me a negative square root of 3. And I go back to my special family of angles and I recall that that is negative pi over 3, the one that gives me a negative square root of 3. Alright, and that is the set of inverse trig functions for cosine, sine, and tangent.